Now let's talk about another measure in simple linear regression. Remember this StatCrunch output that we have just seen? I mentioned that there is r squared equals to 0.90344, and I said we would talk about it later. And here is where we are going to talk about it. So this value is called r squared, or the coefficient of determination. They are the same thing. So the coefficient of determination and the r squared are the same thing. So there are several ways to calculate the r squares, but since we didn't talk about a whole lot of this simple linear regression, so what we are going to use is use the correlation to calculate this r squared. So this coefficient of determination of r squared is calculated by using the coefficient of correlation that we introduced at the beginning of this handout and squared. So if you take a look at the example of this pH and arsenic regression line, the R that we have calculated is negative 0.95, and the R squared will be this R squared, which is approximately 90.3%. That's what's shown on our StatCrunch result. So what does this R squared mean? What is this talking about? So it's talking about the proportion of variation in y that can be explained by the linear regression equation of x. Let me write this down first, then we will talk in a little bit more details about what that is. A measure of the proportion of variation in y that can be explained by the linear equation of x. So what does that mean? For example, in our pH and arsenic removed example, we are trying to study the relationship between the pH value and the arsenic being removed, right? So we are trying to explain the change of arsenic being removed by the changes of pH values. And this is a good explanation, right? We fit a pretty good linear regression line, but there are still, some changes in the arsenic percentage of arsenic being removed that cannot be explained by the changes of pH value. So the variation of y could be decomposed into two parts. One is the variation of y that could be explained by its linear relationship with x. The other part is some other random reasons or errors or anything that cannot be explained by the linear relationship between the x and y. Let's think about another example. So suppose we are trying to explain the BAC count, which is the blood alcohol count, using the number of beers that you have drunk. Now, we would fit a regression line, and we could predict what's the BAC in a person could be. Say, for example, 6 bottles of beer. But you could also reasonably understand that if you are going to randomly select 5 different persons and they all drink 6 bottles of beer, their BAC shouldn't be the same, right? They may vary a little bit. Someone may be having a higher BAC, someone may be having a lower BAC. It depends on a lot of other reasons. The number of bottles of beer they drank is one reason, and they also depends on the age of the people, the gender, and whether they have food already or not. So the changes in the blood alcohol count could be explained by 2 parts. One part is the relationship between the number of beers you have drunk and the BAC. That's one part. The second part is all the other reasons that could be used to explain the changes of BAC. And this R squared, coefficient of determination, measures the proportion of the variation in the Y that could be explained by the linear relationship between X and Y. That is, the changes in the blood alcohol count that could be explained by its linear relationship with the number of bottles of beer it has drunk. So this R squared is usually expressed as a percentage. So instead of saying the R squared is 0.9034, we are usually using a percentage, which we are going to say is 90.3%. So the interpretation would be about R squared percent of the variability in Y can be explained by its linear relationship of X. Now, in our example here, we would interpret it as about 90.3% of the variability in the percent of arsenic being removed can be explained by the linear relationship of pH. So R squared is talking about the proportion of the variation of Y that could be explained by the linear equation of X. Now, let's take a look at 2 graphs. Suppose this is a graph. This is another sample. Which one do you think is going to have a bigger R square? it would be this one, right? So suppose this is 1, this is 2, then the r squared of 1 will be larger than the r squared of 2, because the points here are more clustered around this fitted line, which means most of the variation in the y could be explained by this line, right? Well, in this example 2 here, you could see the points, yes, they still do have a linear pattern like this, but they are more, scattered around the line. It's not very clustered. So that means the proportion of the variation in y could be explained by x, but there will be more percentage comparing to the graph on the left that could be explained by many other reasons, because the data points are not that clustered around the line. And if you think about in another way, using the correlation coefficient, the small r, we have talked about it. This one is having a bigger r, the small r. This one will have a smaller r, because this one is having a stronger linear relationship between x and y. This one will have a little bit weaker linear relationship. So this one on the left will have a bigger r squared. So this is the coefficient of determination. Now let's take a look at additional example of simple linear regression on the next page. Again, if you haven't read the question yet, you could stop here and watch the video after you've read it. The data of PSA has been posted on Moodle as well. Using the data provided, you could get this data scatter plot and the output and as well. So we will go ahead to talk about it. First, describe the scatter plot. There are 3 properties of the scatter plot that we are interested in. That's on this page 2. We examine 3 properties: the form, the strength, and the direction. So let's take a look at this scatter plot here. So the 3 properties: form is roughly linear, right? It's a linear trend. The strength, how clustered are the points to this linear line? Not very clustered, right? So the strength is kind of weak. And the direction is positive. So this is the scatter plot. Second, state and interpret the value of the sample correlation. The sample correlation is calculated here. This this r without squared, this correlation coefficient 0.035. So that is saying there is a somewhat weak positive linear relationship between PSA egg level and prostate weight. Last question, use the fitted line to predict the prostate weight with PSA level of 43.5. So then you need to fit a linear regression line. So the fitted regression line would be y hat equals your beta 0 hat 33.09 plus the slope 0.508 x. Now you could use the data provided to check on the assumptions. Check assumptions of simple linear regression. So this is for your own practice. When those assumptions are met, then you could go ahead to plug in the x equals 43.5 into this equation line to calculate the y. One thing that you need to pay attention is, to make sure that this 43.5 is within the data range. And if you take a look at this scatter plot here, yes, this is within the data range because it looks like it's from 0 to 60, right? The range is from 0 to 60. So this x equals to 43.5 is within the range of the data. So we plug in x equals 43.5. And this is going to be roughly 55. Okay, so this is the end of this video, and this is the end for this handout 13, and this is the end for the lecture for this entire semester. Thank you so much for your support, and I really appreciate it. Your final exam information has been posted on Moodle, so please check on it. And if you have any questions, feel free to stop by my office hours. Okay, bye.